So we have so far discussed about basic communication, okay, and the course name is analog communication, so of course we'll be slowly going into analog communication, but we have so far discussed the modules of communication, that's the transmitter side, receiver side, and how a transmitter side, receiver side communicate to each other. So today what we'll see that what a particular communication system requires. So it generally requires two things, or if we try to analyze it, we really require two things. One is called signal, so little bit of understanding of signal, and the other part is system. So basically we were talking about a transmitter followed by a channel and then a receiver, right. So this transmitter and receiver, that's actually part of system, and whatever we put as input to the transmitter side, that's actually signal, and what that transmitter does, that system actually operates on signal and produce another signal. This is how it, and then the signal propagates through the channel, goes to the receiver, again receiver is a system, it operates on that signal and generates something which is desirable, okay. So this is how it the communication goes through, but let us try to understand. System probably we'll discuss later on, it's probably the hardware that has to be designed which will do some desired operation, but initially we will be more concerned about signal. So what is signal? Signal is something where a particular parameter, let us say it might be, if it is electrical signal, probably it is the voltage or current, okay, which varies with time, and this is the trace with respect to time. So how it varies with respect to time. So let us say if I just put it as a function of time, so let us say gt, and it varies with respect to time. The signal is actually the description, entire description over the time of our concern. If the time is truncated, let us say it starts from t1 and ends at t2, so it is within the time limit t1 to t2, whatever the signal trace, or let us say we are talking about voltage or we are talking about current, so it is the amplitude of that thing. So that is actually a signal description. Now signal can be of multiple pattern, okay, and it can be, means we are here probably in communication system or in communication analysis, we are talking about time varying, or the independent variable is time. It is not necessarily a time always, it might be a spatial variable, okay. So even a signal might be just like let us say in television, the pixel values, okay, it has a spatial variation. So in a two-dimensional space, like in television screen, at every location, what is the signal strength? So there the signal is actually a, means independent variable is space, whatever it is, 2 coordinate. If the space is taken as 3 coordinate, it's a volume, then it should be 3 coordinate. So with that space, how the whatever parameter that we are discussing about, how that varies, okay. So that's, so signal can be of means it can vary with respect to anything, but for our case or for our purpose in communication, we will be mostly discussing about signal varying with time, okay. So now let us first try to see how do we, means anything we define, suppose signal we have defined the way we have defined right now, so that must be parameterized, that means there should be some measurable quantity in that signal, okay. So how do I, suppose I give just a signal, let us say this is gt, okay. Now if I just say that let us say it is defined from t1 to t2, rest of the part we do not define it, we can take it as 0, okay. Let us say this is the signal definition. Now how do we actually measure some parameter of this signal, or how do I characterize this signal? One way is this graphical or pictorial depiction, that is all right. Can we give one parameter to measure some property of this signal? So that one important property is probably the energy of the signal. We will see that has a big consequence, later on we will see that, okay. So how do you define energy? This is something very easy. If you take gt as voltage and if you pass it through a unit resistance, probably you will be able to calculate that. It should be just g square t and you integrate it, right, from t1 to t2, okay. So that is actually the energy of this signal g, Okay. So as long as it is time bounded, probably we can integrate it from T1 to T2. That's fine. We'll get some value, and that's actually characterizing. That is a specific property of a signal. Different signal will have different things. It does not mean that every signal will have a unique energy. Okay. Multiple signal might have same energy. It's just that integration value has to be same for different signal. Okay. If it is not time bounded, then the integration goes from minus infinity to plus infinity. It might happen that this might go to infinity. So a signal might also have infinite energy. That's possible. Okay. So this is one way of characterizing a signal. The other way of characterizing a signal is like this. Suppose the signal we are talking about, it's a sinusoidal. Okay. So it goes like this, something like this. It stretches from minus infinity to plus infinity. Okay. So of course, if we try to measure that energy of this signal, you can immediately see that will go to infinity. Okay. So if I just put this sine square, suppose the frequency is omega t dt, and suppose it has an amplitude of a, so it will be a square sine square, and then if you just integrate it from minus infinity to plus infinity, this is going to be infinity. So this is one example of infinite energy. Okay. Then actually I have failed to characterize this because it's going to infinite energy. Any sinusoidal I will be drawing, suppose I draw it with some other omega, so it will have different frequency, and again I try to characterize it, it will just have infinite energy again. So basically what has happened, I have failed to characterize the signal with respect to that particular parameter that I have defined, that is energy. Can we do something else? Can we put another measurement parameter which will characterize this signal? So that is called power. So whenever we are talking about power, what we generally say that we'll take the overall signal energy and we'll also measure the time and we'll divide it by time. Okay. So it's like this. Suppose I have signal g, so g square t I integrate it from minus t to plus t, okay, and then I divide by 1 by 2t, and then what I do, I put a limit t tends to infinity. So that means by this, from minus t to plus t, I calculate the energy of the signal, I divide by the time period which is 2t, so I get the power of this signal, and then I stretch time to infinity. That means I capture the whole signal, right. So this is the power of the signal g. Okay. So this is another way of characterizing a signal, wherever you can see that some of the signal which has infinite energy, that might have finite power, like this one. Sinusoidal, if you just try to do, it will be just means whether you do it for the entire t or you do it for one period, and whatever calculation you get, it will be the same, because that just keeps on repeating. So more number of g square t you get, that many number of t also you will be getting. So it will get balanced and you will get similar power. Okay. So accordingly we will classify signals later on, so that part we will see, but these are just two parameters with which we can actually characterize a signal. This is something I wanted to tell you. Okay. So the next part is how do we classify signal. So the classification. Okay. So one way to classify is, see, any signal we were describing, we were having a independent variable which is time. Okay. For our case, it might be other things also. So for our case, at least it is time. So whenever we classify the signal with respect to time, we can say there are two things. One is if I take it in discrete time, that means the signal is defined in discrete time, and the other one is the signal is defined always, that is continuous time. Okay. So I can have a continuous time signal versus a discrete time signal. Okay. So the typical example is the GT we have drawn, or even sinusoidal you can put, that is a continuous time signal. Okay. Instead of that, if I just sample this signal at different location, So, let us say this, then this, then this. In between, suppose this is time t1, this is time t2, this is time t3, and so on. So, this particular signal is only defined at time t1, at time t2 and t3. In between, there is no definition of that signal. So, this is called discrete time signal. Okay. We will be encountering this particular kind of signal because we will be doing sampling of a signal, that you will see later on. This is a typical way of representing a signal. So, that we will be dealing with this later on. And the other part is continuous time signal, where signal is defined at every time instance between the limit we are considering. Okay. So, the second way of classifying a signal, now we had this independent variable time, we also have this dependent variable which might be voltage for our case. Okay. So, the signal can be also classified with respect to that. The voltage can be discrete levels or it can take any value. Okay. So, accordingly we will be talking about analog signal and digital signal. Okay. So, analog signal, that is very important for our analog communication, where mostly we will be dealing with analog signal. So, do not get confused with respect to analog signal and discrete time or continuous time. It does not mean that analog signal has to be always continuous time or discrete time, it can be anything. Only thing is that it will be analog or it will be classified as analog signal if the voltage level or whatever that dependent variable we are defining, whether voltage level, current level, whatever it is, whatever we are measuring, that can take any value in a particular range. Okay. So, if it can take any value, there is no restriction with, in that, or it is not taking some discrete values, then it is called analog signal. If that is not the case, it only takes few discrete levels, voltage levels, then it is a digital signal. Typical example of digital signal is binary signal, where we are probably transmitting 0 volt and 5 volt. Okay. So, it only have 2 levels. So, that is why it is called binary. You can have other ways of representing signal, multiple voltage level you can put. So, accordingly those are also characterized as digital signal. Okay. Only thing is that the levels, number of levels are more. Okay. So, that is another way of classifying signals, and do not get confused with the analog signal, digital signal, or continuous time and discrete time. The other part is, which we will encounter quite a lot, this is periodic signal and the counterpart aperiodic. Okay. So, what do we mean by periodic signal? It is like this. Suppose we have a signal GT which characterizes this or which has this quality, that if I translate the signal by a particular value t0, it looks alike. That means, in time if I shift the signal, overall signal, if I shift by t0, okay. So, whichever direction, it might be plus t0, it might be minus t0. Okay. So, whichever direction I shift the signal just looks similar. The typical example is sinusoidal, if it is defined from minus infinity to plus infinity. Okay. So, if you just shift by one period of a sinusoidal, it will just look same. Okay. So, if this particular criteria is satisfied, then we call that particular signal a periodic signal. You will see this periodic signal also will play an important role in terms of signal characterization. Today only we will discuss about Fourier series. You will see periodic signal has a big role to play in Fourier series, the way we represent signals. Okay. So, that is one thing. Of course, if a signal is time bounded, it cannot be periodic, because if a signal is time bounded, it will definitely start from somewhere. After that, suppose it has a periodic nature, but whatever it is, if I just translate it, it will either start from somewhere, it will end somewhere. If I just shift it, then at least either the last or beginning will not match. So, for a signal to be periodic, always the criteria is signal must be stretched to minus infinity and on the other side plus infinity. This has to happen. Whichever is not fulfilling this criteria, that is called aperiodic signal. All other signals are aperiodic signals. If I just put a pulse like this, okay, this is nothing else is defined, from minus t0 by 2 to plus t0 by 2, it is like this, the signal is defined as this. So, this is a aperiodic signal, because whatever shift you give, you will never get back the same signal, that is not possible. If this same pulse is repeated after every maybe let us say t0, then probably if it is repeated and if it is stretched to minus infinity to plus infinity, then it is again a periodic signal. So, that is the difference between periodic signal and aperiodic signal. Next, I am just giving all the definition. You will see that when we will be discussing the properties of signal, these things will come back. So, next is energy signal and power signal. So, what do we mean by energy signal? We have already seen that signals can be characterized by two parameters we have defined. One is energy of the signal and the other one is power of the signal, defined by if signal is GT, defined by EG and PG. We have already seen that. Okay, we have characterized that. So, if for a particular signal energy is finite, okay, so that means it is less than infinity, and power is 0. If this criteria happens, most probably you can see already the signal must be truncated. It should be limited in time. It should not stretch to minus infinity plus infinity, and somehow the energy is also finite. If it is truncated, probably we can always calculate the energy if it is not going to infinity. Okay, in between the signal level is not going to infinity. If that is not happening, all the signal levels are finite, then if time is also truncated, then probably we will be able to evaluate the energy. It should have a finite energy, and the power automatically, because time can be stretched to infinity, and if I divide by that time, of course power will become 0. So, those signals are called energy signals. Mostly energy example of energy signals are time truncated signals. So, whichever has a finite duration, those are generally the energy signal, and the other criteria is the signal level, be it voltage or current, it should not go to infinity. Okay, then it is energy signal. The power signal is all those periodic signal we are talking about, where the energy goes to infinity, because for all those periodic signal, if you calculate energy, that is always going to infinity, but the power is finite. Okay. So, that is actually the example of power signal, this is energy signal. We will see the difference between these two. It is actually, if you see, almost its periodic, aperiodicity has something to do with energy signal, power signal, how do you characterize them. Okay. And the fifth part, which is also an important part, that is where will be actually our communication will be mostly concerned with that. That is called deterministic signal and random signal. So, deterministic signal means that the entire time duration I know exactly how the signal behaves. Okay, so, I know the levels or the level it attains at every instance of time. If that is something I do not know, whoever is characterizing the signal, whoever is analyzing the signal, if that person does not know about what will be the value of the signal at a particular time instance, then we call that as random signal, or we characterize that as random signal. So, if I do not know the value of that signal, then what we are doing here? And I will also give you a typical example. Noise is a typical example of this random signal. So, what happens, even though we do not know exactly what is the value of that signal at different time instance, but what we know is the statistical property of that signal. So, that means we actually know that if the signal level is defined by a random variable, what is the PDF of that random variable. So, these are the things and some more things, of course. Right now probably we have not discussed about that. So, when we will be dealing with this in detail, probably we will be knowing that what exactly is required to define a random signal. And deterministic is what we know, like sinusoidal, pulse train, or any kind of just a single pulse. So, these are the deterministic signal, where we know the definition of the signal for the entire duration. Okay. So, this is typically means what we talk about signal and the classification of signal, different kinds of signals, how do we classify them. So, these are the typical example of that. So right now what we will try to do, which has been done many years before by Fourier, that can we have a different representation of signal. So we know the time representation of the signal. Can we now try to characterize the signal in a different way, a different representation altogether of the signal. So this is what we will try to appreciate. Whatever Fourier has done, what came into Fourier's mind and how he logically developed that methodology, we will try to explain that. Okay, so that will be our next target. So what Fourier have seen at that time, signal is almost similar to vector. So we all are aware of vectors. So what we will try to do, first we will try to characterize how do we define vectors, and then from that vector analogy we will try to build up the theory of signals which Fourier has developed. So this is something we will try to do now. So in vector theory, what we know that suppose we have a vector, let us say this is G, okay, and then we have another vector that is in another direction, let us say this is X. Okay, so these are two vectors in different direction. Okay, in vector few parameters I will define, probably just for recapitulation, most of you all are aware of this. So I will just define. So whenever we say a vector space, it has a dot product defined along with that vector space. So that what we mean by dot product, the definition of dot product you already know. So if I say G X, this dot product I want to get. So generally it is this G, that is actually the amplitude of G. Okay, so it is actually this value into amplitude of X into in between whatever angle they have. Vector means it has a direction, so they must be having some angle between them, cos of that angle. So this is typical concept of vector, right, the dot product concept. Okay. If we try to do dot product of the vector along with itself, so that must be distance multiplied by his own distance. So distance square and cos theta, theta is 0 because it is the same vector. So theta 0, so cos 0 is 1. So generally distance square is characterized, and distance square comes from dot product only. So a vector dot product with itself gives me the distance square, right. So this is something I know already. Now what I will try to do now is something new. So basically what I am trying to do, suppose I have a vector x which is a known vector, let us say this vector I know already. Now I have another vector G I want to represent with respect to vector x. This is just a representation. So I have an arbitrary vector, I am trying to represent best representation that I can do. I want to represent this vector G with respect to this vector x. What will be my representation? So basically if I have to represent with respect to this vector, I will be always in this direction. I cannot go any other direction because I have to represent with that vector only. So I can only put a scalar multiplication to that vector, right. So let us say that scalar multiplication is C. So I approximate G with C into x, where C is a scalar. Okay. So now it depends on the value of C, what value of C I put. So if I put C this much, okay, then it will be, let us say C is defined in such a way that C into x is up to this, okay. Or I can also define it in such a way that C is up to this, okay. So this is Cx, and here this up to this is Cx, okay. So I wish to represent G with respect to x. So I have come up with this value Cx, right. So how good my representation was? I need to know the error of this representation. So error must be how much I should add with Cx to get G, that should be my error. So if I just put this vector which I call E, that must be the error vector. So I can immediately write in vectorial term G is equal to Cx plus E, where E is the error, right. So if I just put it this way, then my error will be this one. If I just put it this way, my error will be this one. Now it is very trivial to see how do I minimize the error. When it will be minimized? When the vector gets its projection on x. So it will be exactly perpendicular. So C is chosen in such a way that I get the projection of that vector immediately on that point. Okay, so that should be my best choice. I cannot do anything better than this, right? So this is what I wish to do, and this is how I minimize the error. See, I am just trying my best to represent that vector given this other vector. I am not doing anything else. Okay, but you will see with this a beautiful representation will come along. Okay, so this is what I can do, and of course this becomes my error. So that is the best error I can do. Now whenever this error is the best one, then what I can say about this means how do I evaluate that particular C where the error is minimized, right. So this is something I wish to now derive, right. So whenever I am trying to derive that, what I can say that let us say this C x, this particular value, when the thing is minimized, the error is minimized. What is that? That must be that value of g, okay, into cos theta, because it is exactly projection. So g into cos theta must be the Cx, okay, the modulus I am talking about, of course. Now I am not talking about the direction, because I have already taken the theta. So C into x must be g into cos theta. So this is true, this should be the case. Now what I will do, both sides I will multiply by the modulus of x or the length of x. So C mod x square, that must be mod g or norm g norm x cos theta, right. Now go back to our earlier definition. So we get C, this is nothing but dot product of g and x. So that is g and x dot product, and this is nothing but dot product of x with itself. So this is how the optimal C can be represented. And when we say a vector g is orthogonal, that is the definition of orthogonality. When we say a vector g is orthogonal to x, if g cannot be represented by x, that means the projection will be, the value of C will be 0. So I cannot represent that vector anyway by the other vector. If this is happening, then only I can say they are basically orthogonal. So immediately what should happen? C should be 0. So that means the g vector should be directly perpendicular to this x vector, and I will not be able to represent anyway. Okay, I cannot characterize even the error because I do not have any representation. C value is 0. So if C is 0, if C has to be 0, immediately I can see the condition of orthogonality. That means g dot x must be 0. So that is the famous orthogonality condition in vector. All these things you already know. I just have demonstrated this to so that you can appreciate that it is nothing but a representation technique that we are trying to employ, where we are trying to, all we are trying is trying to minimize the error of representation, nothing else. Okay. Now what I will do on this paper, which is a 2-dimensional thing, I will just take 2 vector, and you will see very nicely the entire representation will be done. This is how the coordinate system has been designed. So in the next section of this class, we will try to do that, and then we will go to signal with this analogy.